Now for a biased transistor, for example, classically biased using a single power supply by fixing VBE, this circuit, right? The Q point, base to emitter voltage, collector current, base current, collector to emitter voltage need to be stable, need to be fixed in the absence of AC signal, right? But what happened? We already know that we have a sharp relationship, the exponential relationship between collector current and the base to emitter voltage, right? So if for some reason, for the fluctuations of in this input signal or temperature or something, if this VBE is changed, right? So that is, even that change is small and unwanted, small change in VBE will result in a large change in the collector current, right? Because of the exponential relation between these two things. And that change in collector current at the output side will change the collector to emitter voltage, right? And if we take the classical biasing single supply scheme by fixing IB here, same, right? The sharp relationship between collector current and the base to emitter voltage, or IB beta times, right? Beta is very high, so usually very high, right? So IB time beta is IC. So if a small variation in beta, then even the same base current will be translated as different collector current because of the variation of this beta, right? Even for the units of the same device, right? It means if you replace the transistor with the same model, but because of the manufacturing error or tolerance, the beta could be different, right? So for that change in beta will result in a change in current, collector current at the output side, right? And that will be translated as change in collector to emitter voltage even without any injection of the AC signal. So your Q point is not stable, right? So both these classical biasing schemes are considered to be bad, and neither scheme is recommended for precise application. For precise applications, we need to explore other biasing schemes. But for basic introduction of transistor biasing and for non-precise applications, it is in the studies, right? So, but there are parameters. If we critically understand and take into account while biasing a transistor with these classical techniques, we can still get near to precise signals. So let's start with this one, right? So what we want our transistor parameters to be stable in the absence of an AC signal, right? So it means our design seeks to stabilize either IE or IC. We want to stabilize IC. So same thing is IE, right? Because they have a relation of alpha, and alpha is very small. So if you want to stabilize IE, is the same you are going to stabilize IC, right? So let's stabilize IE, and effectively we are going to stabilize IC, right? And we know that this is the equivalent circuit, Thevenized form of this circuit, right? So if we write a loop equation at this side, then we will be having VBB is distributing amongst RB, base to emitter junction, and RE, right? So voltage at the base resistor, base to emitter voltage, and emitter resistor voltage would be the sum of this supply VBB, right? And we all know also write VRB as IBRB and VRE as IERE, right? And we know that IE is equal to IC plus IB. From that relation, we can find I is equal to beta plus 1 into IB. We already derived that, right? So we can replace this IB by IE by beta plus 1 to IB. So we have only IE current left in this equation, right? Because we know that these all are related with a single equation. So if we find the relationship for IE at the one side, then we can get this relation, right? So now let's see what are the parameters need to be considered to make this IE stabilized without applying any AC signal, right? In the absence of AC signal, this IE should be stable. So how it can be stable? If we take VBB greater than VBE, then it will be less sensitive to base to emitter variations, right? So it means for a small VBE variations, this will be absorbed by this consideration. And here as well, if we take RE greater than RB by beta plus 1, then this relation will be less sensitive to beta variation, right? If this factor is very small, then the change in beta will not affect much to this relation, right? And to the IE and to the stability of the Q point, right? So it means if you take this, you can make your relation insensitive to beta variations. Now let's see in detail these two considerations one by one and see whether we are neglecting some other requirement if we take this or this recommendation, right? So for example, if we consider this, then do we have any other requirement that is neglecting? Writing a loop equation at this side, right? So we know that the Kirchhoff voltage law says that VCC, VRC, VCB, VRB, and VBB, right, are in this loop, right? So we can write the equation as VCC minus VBB is equal to VRC plus VCB. Of course, there would be VRB here, right? So for a value of VCC, for a given value of VCC, if we increase VBB, right? This constraint said that VBB should be very high than VBE, right? So how much high? So for example, if we take VBB high for a particular value of VCC, then this difference will be very less, right? For example, if we take VCC as 10, VBB as 1 volt, we have a difference of 9 volt, right? But if we take VBB more higher, they said that must be much higher than 0.7, right? So, for example, if we take this as 3, then 10 minus 3 would be 7. So it means you would be having a less difference here if we increase VBB to accommodate this constraint, right? So it means this difference in voltage would be distributed in these two things, right? So it means by increasing this thing, you are reducing the voltages across RC and voltages across collector to base junction. Of course, across this RB, but it's not at the question at this point, right? So it means we are actually lowering the sum of voltages across RC and across collector to base junction, and do these reduction in voltages across RC and VCB by increasing the value of VPP to accommodate this suggestion. Do we have any disadvantage of this? Yes. As VRC is required to be large to have a high voltage gain, right? If VRC would be large, then for an input AC signal, you would be having a reduction in current, then voltage across this resistance will be reduced, and then collector to emitter voltage will be increased to have a voltage swing, right? But if you have less voltage across this one, then you would be having less swing, right? Similar is the case for collector to base junction, right? So for a particular VBE, for a particular value of VCB means you are talking about a particular value of VCE, right? Right? If you fix these two terminals and you talk about this one, so you can talk about this one with reference to this one or this one. So it means for a particular value of VCB, it means you are talking about VCE as well, right? So it means VCB should be large to have a large signal swing before the saturation come, right? This one before the, for the swing before the cutoff occurrence, right? So this one is the large signal swing before the saturation, right? Please recall and revisit the Q point fluctuation for an input AC signal, where we have analyzed by drawing all the signals on the characteristics curves, right? So it means we are having conflicting requirements, right? This said that VBB should be increased to have a stable IE, right? For temperature and other variations, but if we increase this thing, we are actually lacking of signal swings, right? So we have a conflicting requirement. So but we should be having a trade-off solution, right? We have to compromise. It means we don't need to, we can make this high but not much high, right? And we can have a large signal swing but not much large. We have to make it a little small to accommodate this constraint as well, right? And we can see this, many experience have shown that a rule of thumb to accommodate these conflicting requirements, this and this, we need to distribute the voltages across VBB, VCB or VCE, the same thing, right? And VRC should be 1/3 of the VCC, right? So this is the rule of thumb, right? Now you can do your homework number 2 by using this thing, right? Where we need to design a common emitter amplifier with emitter resistance. You have to do that, right? So now let's consider the constraint at the emitter and base resistances. Here, to make our relation insensitive to beta variations, we need to make Re much higher than Rb, right? So it means we have to increase Re or decrease Rb. If we decrease Rb, we need to decrease R1 and R2, right? So now let's see, we have any other conflicting relation constraint? Yes, reducing R1 and R2 means we will draw more current from the power supply for nothing, right? It's just pass through, just to make a VB at the across the R2 resistance, right? And by lowering the R1 and R2 values, we are actually reducing the in